Welcome to our discussion on logarithmic functions and their properties. Today we're going to figure out how to use and apply the definition of a log function in order to graph it, model with it, use the properties of it, and then use the change of base formula so that we can work with other exponential functions. So first let's look at the function and its graphs so we understand basically what the log function is. So before the development of calculators and computers, certain basic arithmetic computations, such as just raising something to a power or taking an odd root of something, I don't mean odd like the number's odd, I mean something other than a typical square root, were very difficult to perform. They could be performed relatively easy using logarithms, which were developed in the 17th century. Now, we may express the equation x equals a to the y, that's kind of our typical exponential function, in the form y equals f of x by defining a logarithmic function. Because logarithmic functions are literally the inverse of an exponential. So what that means is we can define the logarithmic function to be y equals log base a of x, has a domain x greater than 0 and a base a, and is defined by a to the y equals x. You'll notice that a to the y equals x is different from a to the x equals y because the x and the y have traded places. Well, when the x and the y trade places, that's an inverse. That's what an inverse function does. So from the definition, we know that log base 3 of 81 equals 4 because 3 to the 4th equals 81. And the way, as students, we think of this is this question is saying this base raised to this power has to equal this number. And of course it does. So when we have log base a of x equals y, we're saying a to the y equals x. And that's where we get this. So one of the main things to learn about a log function is that it really is an exponential function in disguise. And more precisely, it's the inverse of the basic exponential function. So you can always treat logs as exponentials if it makes it easier to work with them algebraically. Here are some typical examples of how you would change things around. Remember, it's always take the base, raise it to the power on the other side of the equal sign, and then set it equal to the number inside the log. Now, if we graph log base 2 of x, we get this fun thing. And if you graphed y equals 2 to the x, right? So if we did, right? So if we put the equals y over here, we get 2 to the y equals x, right? It's the same thing as 2 to the y equals x. But if we switch places with it and make it 2x, 2 to the x equals y, then these are inverses of each other. And if we graphed y equals 2 to the x, we get this function. And inverses, remember, are such that if you graph them, they are mirror images of each other across the line y equals x. And these two, I mean, I'm not a perfect artist, but these two are. So you can kind of visually see how logs are, in fact, inverses of exponential functions. So we can see that every log has a base. Most applications of these logs involve either the base 10, which we call common logs, or the base e, which are called natural logs. And the reason why they're called natural logs is because things that are base e tend to occur in nature more. So common law and natural logs, right, are just base 10 and base e. That's all it is. And remember, the base can be any number you want, literally any number you want that's greater than 0. Okay. So if a certain amount of money is invested for t years at an interest rate of r, compounded continuously, then the future value of said investment is given by this simple formula. S equals your future value. Oftentimes people put FV for future value or A for amount of stuff in your account. I've never really seen S before, but we'll go with S equals P, your starting principal. E is that special number, 2.718, blah, 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 raised to the RT. I know that kind of looks like a pi symbol, but that's R times T, where R is your interest rate and T is your time in years. So the doubling time for this investment can be found by simply setting S equal to 2P, right? Because if we had 2 times our starting principal, it's doubled. And then we can solve it, first of all, by dividing both sides by P. So we just get 2 equals e to the RT. And then we can express this equation in log form in order to solve for T, because we can't solve for T when it's trapped up here as a power. We have to bring it down onto the ground and solve for it that way. So you'll remember that this is equivalent to this, right? E to this power equals 2. So now we have log base E of 2 equals R times T. And if we want to solve for T, all we have to do is divide by R. Well, log base E is the natural log, and we give it this nice little shorthand because we use it so often. We give it this ln for logarithmic naturel. It's the French word for natural log of 2 all over R. If the interest rate was 10%, then of course we put in 0.1, because whenever we're dealing with interest rates in any kind of formulas, we always list them as decimals. And then we can calculate natural log of 2 in our calculators, which rounds to this. That's why this is an approximate. Divide it by 0.1, which gives us roughly this. Or I'm sorry, multiply both sides, top and bottom, by 100 to get rid of the decimal. And then divide by 10. But I mean, same thing. If you just do this divided by 0.1, you get 6.93. So in general, it would say that we can approximate the doubling time for an investment at R% compounded continuously with 70 over R. You see how this was 70 over R, where R is the interest rate written as a number and not as a decimal. So that's where this comes from. So we can approximate the answer by 70 over R. And this is called the rule of 70 in economics, basically saying that it takes 70 years to double. Or it doesn't take 70 years to double. It takes 7 years to double, but we can use the 70 years as the starting point, because depending on what the R is, it's going to shift, right? It's not going to be 7 years. It's not going to be, it'll be different ones depending on what R is. But the rule of 70 just tells us we take 70 and divide by R. It's a shortcut. I don't know why they have it, because, I mean, they all have computers now. They can calculate exactly what the doubling time is. But c'est la vie. So let's graph y equals natural log of x. Right? You can do it by plotting a bunch of numbers and then connecting the dots, or you can get yourself a nice little graphing calculator or any kind of other tool. And we can see that some of the generalities of it, we've got its basic shape. It always goes to the point 1, 0, just like the exponential function always goes to the point 0, 1, unless they've been multiplied by a constant. And 1, 0 is the inverse of 0, 1, because the x's and the y's have traded places. You can see that the domain, right, the left and right, is just all positive reals, because you can't plug a negative number into it. It comes and hugs this, just like the exponential function comes down and hugs the y-axis, so its range is all positive numbers. The range of this is all numbers, right, because it goes all the way down to negative infinity, all the way up to positive infinity, just like the domain of an exponential is all reals. So you can see that when you have inverses, domain and ranges trade places as well. And we have an asymptote of the y-axis, just like with the exponential, we had an asymptote of the x-axis. Again, inverses. Okay, let's see how we can model with these things. Our first example is life expectancy. The lifespan of people in the United States depends on their year of birth. The table below, where x equals 0 is 1900, gives life expectancies. You can see that life expectancies are going up, but they're going up at a slower and slower rate. right? They made some big jumps in the beginning, and then the gaps are getting smaller and smaller. So they're having shorter and shorter, right? No gap, no jump there at all. Tiny, tiny, tiny jumps, right? So yes, it's getting bigger, but it's getting bigger at a slower rate. And that's what a logarithmic function does. Just like an exponential function gets bigger at a faster rate, logs get bigger at a slower rate. So you can use technology to find the equation that models the data. And then the National Center of Health Statistics projects the expected lifespan for people born in 2000 to be 77 years, and that for those born in 2010 to be 78.1. And we can use the model to project the lifespans for those years to see, basically how close it comes. Could the expected lifespans for 2015 and 2020, as given in the table, have been found with the model in Part A? So using technology and all those data points, this would be the best fitting a model we could get. Now the government is going to have a much more robust model. They're going to have more data points. They're going to fit a more complex function to it. So they're going to get more accurate results than we're going to get from this simple logarithm. So x is the number of years since 1900. And this is a picture of our model. You can see that it fits the data fairly well. Now, using that model, we can plug things in to answer part B, right? So for the year 2000, the value would be 100, because remember, x equals 0 was 1900. So we plug 100 into that function, and we get 76.9. 2010 means we plug in 110, we get 78.3. And these are pretty close to their projections. You might not remember what their projections were, but it was 77 and 78.1. We get 76.9, pretty darn close to 77. 78.3, pretty darn close to 78.1. So we could say, yes, the values from the model, they don't match perfectly, but they match very closely. Okay, how about some properties of logarithms? Well, we already kind of discussed these, right? We know that if y equals f of x and y equals g of x are inverse functions, if whenever a pair AB satisfies y equals f of x, then the switched pair BA has to satisfy y equals g of x. Furthermore, because the values of the x and y coordinates are interchanged for inverse functions, their graphs are reflections of each other about the line y equals x, right? We've already talked about this. So for these functions, we get this idea, right, that we see this happening, and we get this point, and then over here, we get these exact opposite points. And we also saw that I showed before that the functions are mirror images across the line y equals x. So we're now just proving basically what we've already been talking about, that these two functions are inverses of each other. So we have log property 1. If your a is greater than 0 and not equal to 1, then log base a of a to the x always equals x. Because think about it, it's saying a to what power equals a to the x. And you go, well, duh, a to the x equals a to the x. To prove this, we could switch things into their logarithmic form, right? So we go a to the y, sorry about that, a to the y equals a to the x. So y has to equal x, and then therefore this has to equal x, right? Because the only time you can get a to a power equaling a to another power is when those two powers equal, right? 2 to the third equals 2 to the x. The only way that would happen is if x equals 3. Now we can use property 1 to simplify each of the following. Well, we know log base 4 of something has to equal 4 cubed, so ergo it's got to be 3. And then we have to remember that natural log is log base e, so we're asking e to what power equals e to the x, and we go, duh, it's x. So this also starts to tell us that, hey, look, if we take log of something, the power comes down, right? Log base 4 of this thing, we get an answer that's 3. Natural log of this thing, we just get the answer that's x. It's a way of peeling the power out and bringing it down onto the base of our equation so we can solve for things. And so that's how we're going to solve exponential functions when we have to solve for the power, is we're going to use logs because they undo the powers. Special cases of our first property is when they're raised to the power of 1 and 0, right? 1 gives us a, 0 obviously gives us 1, because anything raised to the power of 0 is 1. So, right, this becomes 0, and this one's 1. We know that the logarithmic form of this is log a of y equals log a of x, so y equals x. So now we can see that if we take a and we raise it to the same base, right, the log of the same base of something, these undo each other and you just get x. This is showing that they're inverses. A raised to a power of a logarithm of the same base of that thing, the log and the power undo each other and you just get back to x. Just like we saw before, if we do log base a of a to the x, we get x, because if we take the log of an exponential, they undo each other. So this is property 2, just showing that exponential of a log is the inverse, same thing as the log of an exponential. So we could do all these same things and get, okay, this is 4, this is x. Well, now that we have that they work in both directions, we know specifically that they are inverses of each other. Because logs are really just exponentials in disguise, we know that the rules of exponentials should act relatively similarly to logs, and they do. If we have log base a of m and then log base a of n, right? So the bases have to be the same, just like if we had, the bases of a to the x and then a to the y, the bases are the same. So if we have these two things, we know that a to the u equals m and a to the v equals m, right? We just do a to the v equals n, a to the u equals m. So if we do log base a of m times n by substitution, we're getting a to the u times a to the v. The rules of exponents means that we can add those and we just get a to the u plus v. And then we know that when the bases match, it just goes away, right? Because we're saying a to what power equals a to the u plus v. And you go, duh, it's got to be the u plus v. And u plus v, by definition, right, up here, is just log m plus log n. So if we just cut out the middleman, we can see that when we take log of a product, we get the sum of the individual logs, right? So we get log of m plus log of n. We can look at some examples, right? Here's the log of products. We can split it up in log base 2 of 4 and log base 2 of 16. Well, 2 squared equals 4, 2 to the 4th equals 16. And so therefore, we get that it equals 2 plus 4 equals 6. Well, of course, 4 times 16 equals 64, and 2 to the 6 equals 64, right? So duh, we would just do it this way, but we're just using numbers to make it easy to see how it does in fact work. Same thing with this, right, that we could break it up and do natural log of 7 plus natural log of 11, but why wouldn't we just do natural log of 18? We would, and we would get the same answer. Okay, property 4, if we're doing a quotient, we just get subtraction. And we could show you how to do it. It comes from the same rules of powers. And remember that we would have a power over a power. And remember the rule of a power over a power is it's the top number minus the bottom number. And that's why we get the top number minus the bottom number. And then we could play around with these and see that, it works. We could also do log of something to a power. And remember that a power to a power, you multiply those, so that's why we're multiplying. It just becomes the power times the thing. So again, this shows us how when we take a log of something to a power, the power comes down in front and just becomes multiplication, and thus we would be able to solve for that power. So this log property becomes a very important tool for solving exponential functions when we're trying to solve for the exponent, right? When we have like an x or a t or something up there that we're trying to solve for. Here's some examples. You can pause it and look through them. All right, the last thing we talk about is change of base. And sometimes you want to change a base because, as we saw, if we take log of a base that matches the base of the thing we're applying the log to, everything goes away and we just get that number. So if we were taking log base a of b to the y, that's not going to help us so much if we were doing log base b of b to the y. But we can do some change of base stuff to figure that out. So first of all, we know that log base b of x can be written as b to the y equals x. Therefore, we know that log base a of b to the y is the same thing as log base a to the x. We're just substituting these two things because they're equal to each other. Well, we know from the power of logs that if we apply this, the y comes out in front and we get y times log base a of b still equals this. Then we can divide both sides by log base a of b, and here we go. We get y equals log base a of x over log base a of b. And basically what's happened, right? First we had y defined in terms of a base b log. Now we have y defined in terms of a base a log. So it's a way of changing base, right? So it's instead of log base b of x, it's log base a of x, and then all you have to do is divide by log base a of the original b. So it's basically log of the new base evaluating the old base. That's how the change of base formula works in its generic form. So if we look at an example, log base b of x is the same thing as log base a of x over log base a of b. That means we can convert logarithms to base e or base 10. So log base b of x is log base e of x, which is natural log, all over log base e of b, which is natural log of b. And then we can also go to base 10, right? It becomes log. Whenever you don't have a base, we just assume it's log base 10, because since e and 10 are the two most popularly used ones, we gave e its own name of natural log, and then we gave base 10 the honor of not having any number, and then that way any other base we just have to list that number. And we do that just for efficiency. Since we're going to be writing these the most, let's try and do them with the least amount of pen strokes, so to speak. So here's those two conversions. Our last example is showing us how we could do the change of base so that we could actually evaluate these. Because if you don't have a fancy calculator that lets you do logs of any base you want, you just have a basic old scientific calculator, those will only have a natural log button and sometimes a log button. So you need to be able to take these things and convert them into either natural logs or logs in order to evaluate them. So the rule is it's the new log base of the original number divided by the new log base of the original base. We could do both of these in our calculators and we could get this approximate answer. And then we could check it, take 7 and raise it to that number and see that we get 15. And that's everything I've got for you.